Welcome to a lesson with Dr. Powell. Let's take a look at the example that we looked at in the last video, where we were actually rewriting like 3, 2 in the AB basis, and we were writing it in the E1, E2 standard basis over here. Okay, and we did it via matrix multiplication. And pretty much all we do is just rewrite the A and B in terms of the standard coordinates and just write them in columns, and that actually gives us our change of basis transformation. Okay, that goes from this basis to that one. Now, what about if we want to do this in reverse? Okay, what if we started with 5, 1 and we said, well, what is this in the skewed coordinate system? How do we work backwards? How do we go back? Well, this matrix right here, because these guys are linearly independent, and they have 2 coordinates right here. This is actually isomorphism. It's bijective. Its Smith normal form is just the identity matrix. I mean, this looks great, right? Which means since it's isomorphism, it actually has an inverse, which means we can go back the other way. So all we have to do is compute the inverse of this matrix, and that should take us from 5, 1 back to 3, 2, going back the other way. So let's actually do that. Let's come up with what the inverse is of that matrix. Okay, so let's go ahead and see how we will do this. If we have, so remember we have 1, 1, -1, and 2. That was our change of basis matrix. Okay, and we want to find the inverse of this. So now, if you recall our videos with finding left and right inverses, it's really the same idea. You can find either a left or right inverse, and it will be the inverse of this matrix because it is bijective. So both left inverses and right inverses are the same. In fact, it's just one thing that's very unique. So there's only one way of doing it. So we can either use row operations or column operations. We'll use row operations, and we would come up with the row operation matrix by applying the row operations that we need to get this into Smith normal form, which is equivalent to reduced echelon form in this case. And we just apply it to the identity matrix, and this will turn into the row operations matrix, which will give us the inverse. Okay, so let's go for it. Oh, so first row operation will be an airdrop going down this way, just multiply by 1 and then drop there. And so when we do that on this matrix here, and maybe we'll do this in steps here. So we have 1, so 1, 1, and we drop down, we get 0 and 3. Now we do the same thing over here. So we end up getting 1, 1, 0, 1. So because this just adds down to there. Okay, very good. So we got this much so far. Okay, now, but remember, when we're finding inverses, we have to either do row operations or column operations as we go. So we need to keep going. Here, I'll do a row operation. I'll just divide this row right here by 3. Okay. Okay, so I have to do it to the same thing. So that row right there has to be multiplied by 3. So doing that, over here I get 1, 1, 0, 1, and down, this is getting close. And down here, I get 1, 0, a third, a third. Okay, now I just airdrop this way with a -1, and that'll finish me off. I'll have 1, 0, 0, 1, but I have to do the same thing over here. Multiply this row by -1 and add it up to that one. So I end up getting 2/3, -a third, 1/3, and 1/3. Okay, this right here is the inverse matrix to this one. In fact, you could even try it out if you wanted to. We could say 1, -1, 1, 2, and multiply it by, and you can, so this is an inverse. It's actually an inverse on both sides, left and right, because this is this matrix right here is an isomorphism. So we can try it either way. We'll do it on the We'll do it on the left, right over here, though. Let's see. In fact, to make things simpler with this particular matrix, I mean, matrices themselves are functions between things, and functions between things are actually vectors that can be rescaled. In fact, this one can be rescaled nicely. You can just factor, it's like a vector. You could factor out the 1/3 out of everything. So if you factor the 1/3 out of everything, this would look like 2 minus 1, 1, and 1. Okay, now let's go ahead and multiply this. Let's go ahead and multiply this out and see if we actually get the identity matrix. Okay, so all right, now if we think about a column interpretation for multiplication, this right here means take 1 times that column and then just subtract off that one, which means which in this case would give you a 3 on the top. Because it's like 2 plus 1. And then down here, this would actually give you a 0. Then if we say 1 times this column plus 2 times that column, you actually get a 0 on the top and you get a 3 on the bottom. And notice we still have the 1/3, and sure enough, we do get the identity matrix. That was nice. So we did find the inverse, all right? And we also discovered that it's nice to write it this way, 1/3 times that matrix right there. Okay, so let's go ahead and look at this for a minute. All right, so we have 1/3 times 2 minus 1, 1, 1. And let's try this out. So this will put something into AB coordinates, right? Because the other one actually took something that was like this matrix right here, took something that was in AB coordinates and wrote out what it like, so in the skewed perspective, and pulls what it was in the regular perspective. So this does the opposite, puts things into the skewed perspective, so into AB coordinates. So let's try this. If we started with 5, 1, right? Let's see what we end up getting. We should get 3, 2 like we had before. And let's see if that's what we get. So let's think about this. I'll do 5 times this column. So 5 times this column would be, you can think 10, 5, and 1 times this column, like -1, 1, add them together, and I end up getting 9. I end up getting 9, 6. But remember, multiply by a third, and the result is simply 3, 2, just as expected. Okay, so great. So we've just discovered how we can go back from one coordinate system and then to the other. All right, so we've successfully written our point that was in regular coordinates in the skewed coordinate system. Then we have, if we use this matrix on this vector, we can go back and write it in regular coordinates. Thanks for watching.